Hello, welcome to lecture 60 in the video 60 in the lecture Advanced Mathematic Modeling. We are looking at the West-Brown Enquist theory for metabolic scaling. We assume we have this fractal branching network, we have the geometry of the vessel, and in the last video we calculated the total volume of the system, and we had the sum of all volumes of vessels of all sizes. That was a geometric series which we could work out, and we could assume if this product here is a small value, we could simplify this, and then we found that this scaling factor of the volume of a capillary to the total volume of the aorta needs to be proportional to the body mass, and then we could plug in this into something we had before, and we could find a relation that our power law exponent is related to our three fundamental quantities, the branching factor here, the reduction in length and radius. And now we need to come up with some formulas which relate these quantities, and this we want to do in this video now. Okay, so first let's look at the at the betters. So the ratios of the calculation of branching ratios. So the first we were interested in this better. This was the radius at the next level of the branching, the radius of a vessel at the next level divided by the radius before. And now the question is, how do we get to this? And here the assumption is, now we need to make some more assumptions about our supply network. And the idea is, if we have here a vessel, and now we branch this off into some smaller vessels, and we have here smaller cylinders, so to say. And here we have an RK plus 1, or maybe this sketch was not too good, so maybe try. So this was the vessel at one level, and then we had the vessels at different levels at the next level. And then we want that the flow should go through from all the blood which comes from here should go through all the systems, and that this would be possible if the cross section or the area here should be the same. The same before and after branching. And when you look in the autonomy, that's really a good assumption. So when you look at smaller vessels at such a branching, and then the smaller vessels have a smaller radius, but this radius is related to the radius of the larger vessel in such a value that the areas here, the red areas and the blue area, is the same. So this means the cross section, the area P RK squared, should be n times the area at the next higher level, because we have n of such areas and every area has a smaller radius. And then directly from this we see a relation that better, so rk plus 1 divided by rk should be our branching factor to power 1 minus 1 over 2. So simply the fact that this area should be conserved relates these two of these three parameters. So remember here we said we have three fundamental parameters which determine the geometry of the fractal and then give our exponent. And now we see two of them are already related. And this came when we were looking at the radiuses in such a branching. Now what's happening if we look at the length of the vessels? And now we can also make an assumption. We look again for volume, but now we don't calculate the volume of the blood vessel itself, but we calculate the volume of the supplied tissue. And so the idea is, if we have here a vessel which has a certain length Lk, then this can support a certain volume here or around this vessel. Yeah, and now we do something similar. As before we said the cross section should be conserved in a branching, and now we want that after branching also the volume of the supplied tissues should be conserved. So volume of the supplied tissue should be conserved. By branching. So let's write down the volume. So the volume, then let's assume we have here a simple sphere. We have 4/3 pi, and then we have this length half to power 3, and then would be the volume of a single vessel, and then we have to multiply it with the number of all vessels at this level, and this should be the same as the volume at the next level, 2 power 3 times the number of vessels at the next higher level. And then now we can cancel a lot of this, and then we come to the relation that our branching factor to power 3, so Lk plus 1 divided by Lk to power 3 is proportional to Nk divided by Nk plus 1, and this equals 1 over n. And then we see our parameter gamma equals n to minus 1 over 3. And so with a similar argument, so that the volume of supplied tissue should be the same independent of what kind of depth in the branching network we are. And so we assume that in this volume here we have only one vessel of this depth in the system. That would be the assumption. So because then we have a space filling fractal, because we have for every scale we have exactly one vessel which is used here. because like this assumption took me some time to understand the intuition behind this, but the idea is that we have here a space filling fractal we have at every scale we just have here in this volume here we have this just one vessel which is supplying vessel at branch at level K, which is supplying the tissue, maybe so some hints what the idea is behind this assumption here, because like this was for me not so intuitive, like this conservation of the cross area. But now let's go back to our formula we had somewhere before. So our fractal dimension was given as this ratio from our fundamental parameters. Maybe let's write this down again. So what was our fractal dimension? Alpha was minus logarithm of n divided by logarithm of gamma beta squared. And now what did we do? We related beta to n and gamma to n. Yeah, maybe let's first calculate gamma beta squared. So gamma beta squared equals gamma equals n to minus 1 over 3 beta squared, then we have n to minus 1, that gives n to minus 4 over 3, and now we can plug in this here in the formula. So alpha, our critical exponent, equals minus logarithm of n divided by logarithm of n to power minus 4 over 3. This gives us 3 over 4 times log n divided by log n, and so we obtain alpha equals 3 over 4. Magic. And so we calculated this critical scaling exponent, which is observed in so many data, by just following very straightforward the geometry of our branching network. We needed to look here at these branching ratios. We had here some assumptions. We needed to calculate the geometric sum of the whole blood volume, and we had some ideas, some assumptions that we have a self-similar fractal, but the branching stops at the end members, and this would be universal geometry or properties which are independent from body size, so the same for elephants and mouse. And then thereby, so by just following this calculation, we obtain this critical exponent. And if you were able to follow this, then congratulations. That's not the most simple calculation, and so like this is all in a nature science paper. So that's this what I did here is in a science paper by these authors in 1997, and even though many biologists know about this paper, I would say most are not able to understand this, because the paper is also written not so clearly, or let's say it's written clearly. Probably, I mean, these are genius scientists. It's just technically complicated. But I thought with all the background we had with calculation power laws, thinking in scalings, thinking in exponents, we have everything we need to understand this, and that's this calculation here that we understand this mysterious Kleiber's law now just by calculating. When you look at this, this is very similar how we calculated here this formula, like the self-similarity fractal dimension of this our deterministic fractals. And so like that's maybe a triumph of mathematic modeling here in biology. So with this I want to conclude this lecture. I hope you had fun. I realized, so like we went a long way. So we started with when we look at this lecture, yeah, so we really started from the beginning in probability theory, because I wanted to, this is not treated in all elementary math courses, so I wanted to give you all the same background. So we looked at random numbers, distributions. We learned some tricks like generating functions. So we were considering a lot expectation values and moments. Then we looked at stochastic processes. We had dynamics. Looked a lot at random walks, where we looked at for mean square deviation. We saw how we could model the movement of animals by this. And then we came to scalings, power laws. We looked at Levy walks, anomalous diffusions, where we have like this movements or properties defined by critical exponents. We looked at scale-free systems, and then we came to fractals, self-similarity, and here this allometric theory, metabolic theory. Yeah, so I had a lot of other plans what we could do, some applications, but I think I hinted already that I probably will not have time to cover this all. So of course now with all the techniques and methods that we have learned, there's a lot more interesting stuff which we could directly do now, like models for diversity, for other power law, get richer processes to derive power laws, or problems on networks, epidemic spread. But time was not enough, so I hope you still had fun. If you think that's all interesting stuff and you want to do more, you're welcome to contact me or the tutors in the labs, and we can do some practical, or maybe you want to do your master degree in your master project in modeling in this direction, and then just contact me and we will for sure find some interesting project that you can do. I hope you had fun. Thank you.